on the .NET Service Bus, which is part of the .NET Services Platform, which is part of the Azure Services Platform. I'm going to talk to you today about interconnect and orchestrate services and applications with Microsoft .NET Services. You can tell that was written by a marketing person. Before I start, there's I'll have some weaved in little announcements. We wrote this title and we wrote the abstract before we went into, oops, we're going to ship in November, what we're going to do now kind of exercise, where we, once reality sets in and you know what your test net is, you realize that probably not all the features you have yet shown may make it into the product. So there's some efforts going on to make the pieces that we have really robust. So I'm going to talk a little bit about that while I go through the capabilities. So the talk is going to be in several talks. And by the way, I'm also welcoming all the people who are listening to the recording. Also, yes, you on the bus, and also, yes, you on the train. So I'll be talking first about some of the scenarios, some of the patterns that you can use the service bus for. I'm going to talk about the notion of workflow in the context of service bus. So you're going to see that appear in a particular way. And then I'm going to flip over and talk about some new capabilities that we presented in the March CTP as new capabilities in the service bus for people who are more familiar with the service bus. So there's going to be 3 kind of sample segments. I'm going to start with the first one, a little demo segment. If you are quick remembering things, I will now point you at a little URI, and that will likely not work if you're listening to this on the recording, because that's something I'm doing live here. So clementsv6.servicebus.windows.net, that's my scope on the .NET Service Bus. And there I have a subname, dasblog2. If you hit this from your internet-enabled phone or from your internet-enabled PC, right now from within this room, you will get this page. That's semi-exciting. What's more interesting is that that website is hosted on this machine. And I didn't talk to anybody here about the networking. You will get, through the public internet, through your phone, and this shows that I can't cheat, to this website that's hosted on my PC. I'm going to, as we go back to this, I'm going to go and turn that off, and then if you were going there, you'll see the website disappears. I'm going to make it reappear and do all kinds of things. I'm also going to pull a little rabbit out of a hat. So, they interestingly now moved that slide up on front. It's very important. I get paid by the points you give me. Therefore, you should go and complete the evaluation form and give me very high scores. I will give you a kickback in drinks. My what? I might have to flip what? Okay, good. Am I fine? Don't irritate me. So this session is about mostly core about the service bus. As I said, I'll talk about the workflow in the context of that. So what is it? What's the service bus? What is .NET Services? What it is for? To illustrate this, I have a set of demos, and to make it clearer, I also took a photo of the internet. That is right here. Your personal web property is one of those dots. I optimized the picture a little bit for clarity, but that's the web. There's something interesting about the internet as we know it, about the web as we know it. It is a huge mainframe. And people currently go happily and just upload data into the mainframe. They walk up to the mainframe. They interact with the mainframe. It's a mainframe that's operated in a distributed fashion by a lot of companies independent of each other. But from the model, it's a mainframe because people and businesses live outside of that mainframe. People, businesses, typically live outside in netland. Commonly, every device that you use these days is behind some NAT. It is behind some dynamic IP, which, if you're lucky, is a publicly reachable IP. But it's not deterministic, at least not for you, so you just get it assigned. You will most likely be behind 1, 2, 3, 4 firewalls. Essentially, what we've created with the web and with the internet is a complete reincarnation of the mainframe, where your machine is really just a terminal window into that mainframe. And since we're all happy that it's all centralized, we're all going and upload our pictures to Flickr or Facebook. We're doing all of our communication to Twitter. We're sharing personal details with friends via some public websites. And the question is, does that really need to be? Wouldn't it be nice if personal communication would be happening between two places? Wouldn't it be nice if you could share pictures amongst your family without having to upload those pictures into someone else's website, but you could share them directly? That would be awfully nice. However, there are real networking obstacles that are standing in that way, because it's really difficult to make those connections. So if two people or two businesses want to talk, there are all those obstacles in the way. They can't talk because of dynamic IP, it's not discoverable. They can't talk because of NAT, because you can't really ultimately reach the machine that that person is in, and there's commonly multiple machines behind the NAT, and everything is firewalled. Let's get that out of the consumer space. Let's talk a little bit about businesses. And let's talk about that dot in the middle. What's really important as we move into the age of cloud computing, I would get a star from some analysts for this statement. As we are moving stuff, sort of the processing out to commoditized infrastructure, or as we're running applications, as we're running parts of applications just in hosted environments, how do we actually get back to our core business systems? So let's assume you were an insurance. That insurance runs a website for partners, for their agents, for rate calculation. So you have a set of pages where you enter data about whatever the particular assets that need to be insured, and it's a longish process. It's several, up to dozens of pages of information that you need to go and supply. There's a lot of reference data that needs to be pulled. What you're doing is you're effectively putting together a plan. All of that is UI, and from a data processing perspective, not very interesting. You have a bunch of reference data, and you just put that up on the UI. It's all very important, needs to be done, but nothing happens really. Nothing that is at the core, at the heart of that insurance company is happening at that point. You can take that UI, you can take that application, and happily go and just put that up on Windows Azure. Or you can happily put that up on Google App Engine. Or you can happily put that up on EC2. That's perfectly fine. You got the reference data there, you have the website implementation there, it's all fine. Once you have that package of information and you want to submit that into your system, the question is, how do you get from up there back to your core business system under the assumption that the core calculation engines of an insurance is the heart and soul of that business. That's what that business runs on. Sometimes they're built using, they're hosted in mainframe applications. There are applications that are doing that work, which have been touched in years. That's the heart and soul. That's the core of that business. Is it reasonable that you just take all of that stuff and move it up into the cloud and probably rewrite it? I don't think so. But can you split applications up in a way that you can run parts of that in the cloud and then do the processing in your core business systems? Absolutely, you should be able to. What you need to have, though, is this way to take those business systems and expose them in a way that they can be securely accessed from the cloud system, so that you take your transaction that you've accumulated, your rate calculation job, jam that into the core business system. The core business system goes and does the calculation, and out comes the quote that then is displayed to the customer. So when we talk about software plus services, what we mean is there is value in the assets you run in your own data center. And it would be completely unrealistic to say you have to move all that stuff. We believe that we can run a certain class of applications much, much cheaper at a much, much higher scale than most people ever could. So how do we bridge the gap between the stuff that runs in the cloud that's really fit for a commoditized infrastructure and the systems you have on site? That plus in software plus services, that's the service bus. Let's take another example of where you need to have that intercommunication. Whenever you have assets which are bound to location, whenever you have assets which are not movable just because they need to be at a particular place, how do you establish that connectivity? Let's say a state lottery wants to put little kiosks into convenience stores across the state, thousands of them. And what you can do is you can go there, swipe your credit card, pick a few numbers, out comes an official receipt. You could argue, oh yeah, we can build a web server for that, and you just go to the web server and everything that's displayed there is the web server. Is that really all that happens? Because you need to print a receipt. Just with the web browser, you can't do that. So there is tie-in. It's a local app. Now you can say, okay, that local app just runs there and it does request response to a central server, and that's all going to be fine. Now let's imagine you have thousands of those machines running across the state. How do you look into those machines and see that they're healthy? How do you connect into that box? Let's take another example. Let's assume you have a moving workforce that's always on the go. We can reduce that example. Let's assume you have one boss that's always on the road and probably not very skilled in using any modern technology whatsoever. And so he calls in and says, I have a problem. My application so-and-so doesn't work. How do you get on that computer? Because he sits in Los Angeles, in the Marriott, in the hotel lounge, and all he has is the Wi-Fi. How do you get there? There's tons and tons and tons of scenarios where just that basic connectivity, where you know that there's a network, but you're not reachable, you're not discoverable, there's no way to get to that machine, but that's a problem. Our view on the network, our view on the web is a purely mainframe view right now. There's the mainframe that is the web, and you do request response in, but you're really on the outside. We're all consumers of that. How do we move into that space? How do we make every machine a participant in that? That's our mission. That's what the Service Bus is about. So what we allow for is, first of all, discovery. We allow you to create an endpoint up in the cloud that is discoverable. So the problem that you have with dynamic IPs is, well, you have to have some kind of dynamic DNS system that you go and register your IPs with. That helps you only if you have a public IP address. If you don't, dynamic IP doesn't do anything for you. Now, as things go, dynamic IP isn't really useful because you're usually sitting behind a NAT. And what you're getting is the public IP address of that NAT, And you can assign a name to that, but then from there, getting to a machine or to a service, you got to patch some port, you got to do something to do that. Yes, you can use technologies like UPnP, which you should disable on all of your personal devices because it's not good for security. Because I could write a little program that changes your admin password on your own router through UPnP without me logging on. Just saying. You could use that, or you can go and explicitly manage that and then punch a port down to a particular machine. However, that's on the port level. That's not on an endpoint level. What happens when you want to run very many applications, different endpoints, different communication paths for apps on a single machine? Are you mapping a port per machine? Are you mapping a port per app per machine? How many ports do you want to map? You only have 65,000, and that actually gets very narrow very quickly. And using non-standard ports is something that will not help you at all because there are firewalls in play. Firewalls are really good and useful, as we all know. What are they built for? They protect you from unwanted traffic. Unfortunately, they also protect you from wanted traffic. So if you want to go and expose a service out on the network, you have to open that hole in the firewall. Now, opening that hole in the firewall is kind of a risky thing to do because you're making your system available for any kind of TCP connection onto that port. And if your application is not prepared to deal with some arbitrary fuzzing attack, you're opening it up to attack. So what we do in the service bus is we give you discoverability by allowing you to map your applications into a namespace. I'm going to show you that. We're allowing you to traverse out of your networks that you're sitting in, whether you sit in a hotel lobby or you sit somewhere on a plane, or so with Virgin America, there's internet connectivity. You can actually host a website on a Virgin America plane. I'm actually going to try that tomorrow. I have successfully done that on Lufthansa flights before they shut it down, that service. We'll give you complete bidirectional connectivity between your assets. What we'll also do, using an awesome networking trick that I'm not going to go and elaborate on, you're invited to watch my PDC talk, where I'm going a little more into detail on that. I just don't have enough time for it now, is we're able to create direct peer-to-peer connections between two machines that are behind NATs and behind firewalls. What we do is first we start out with a connection that goes through the service bus, and then we probe the network, the NAT devices in a certain way, predicting their behavior on the next connection, and we'll then go and create a sort of two outbound connections from both sides, which are time coordinated, which will, in 80% of all cases and practically all small business and consumer scenarios, go and snap a direct socket between two sides. So if you wanted to build an application that does things like VoIP, that does things like video transfer, that would be something that would be very useful. Also, generally, and here's one of the little things that we're starting to talk about now. Everybody asked, how are you charging for those things? That's the biggest question. Is there going to be a charge? The answer is, oh yes, because we're here for the greater good, but not quite that much. So yes, you will have to pay for it. How much? Can't tell you because our marketing guys are not quite done yet with all the calculations. However, what I can say is it's going to be consumption-based, which means your entry fee is basically none. And we're going to charge on bandwidth consumption, and we're going to charge probably on per message on some of the advanced features. And it's the pricing I can't go into, but there's similar services in general from other companies, and they post prices, and I don't think we're going to be horrendously more expensive than them. I hope I didn't break into jail. So that's the general scenario, some of the general scenarios. Now, let's talk about mobile scenarios. One thing that's very close and dear to our heart right now in this room, because all the connectivity except for mine is mobile. So if you're just using it, then you may experience that your connections may not be as robust as you want them to be, especially sometimes the wireless walks out of the room and then comes back in. And so how do you deal with situations like that? How do you deal with sparsely connected receivers? We have mechanisms in the service bus. I'm going to show you one of them. It's called the router, which allows you to buffer messages inside the system. So send messages up, have them buffered up, and then retrieve them when you're online. The other mechanism is called the queue, which is a queue. So you can queue messages up for a receiver, and those messages can be dequeued at any time. The difference between the router and the queue, those two mechanisms, is that the router is always push. So we're pushing the messages to you. When the subscriber comes into the router and there are messages pending in the router, in the buffer, we download them into, or we push them to that subscriber immediately. In the queue, it's a pull model, which means the queue just sits there and you go and solicit those messages down. Should the connection break while you're pulling data from the queue, then there's a mechanism for making that robust. So sparsely connected subscribers specifically, or sparsely connected receivers specifically for mobile and Wi-Fi scenarios is something that we have squarely in the radar. Another thing that's very important is event distribution. We have two mechanisms in the system for event distribution. One is similar to UDP multicast, where you have you just have an address, and then everybody goes and just start listening on that address, and if a message comes along, that message is passed on. The qualities are also very similar to UDP multicast in that it's really best effort. The message is sent, and if you receive it, it's good. If you don't receive it, then that message just didn't get there. Because subscribers may come and go, and so it's that quality like UDP multicast. The routers that we have are more in a pub-sub, publish-subscribe fashion. If we can't deliver a message, we will retry. We will retry for a configurable amount of time. You can explicitly manage subscriptions. You have an explicit place where those subscriptions are maintained, and you have influence over the policy of how messages are distributed. In the multicast group, represented through the net event binding that we have, the WCF binding, everything is just multicast, everybody gets it. It's like, as I said, like UDP broadcast or multicast. With the router, you get more control over it, where you have a distribution policy that says all receivers get it, or one receiver gets it. One allows you to go and load balance across a set of receivers. What we're also going to add, and that's going to be, so there's some future here, we're going to go add filters into the routers, and possibly even to the binding mechanism, where you will be able to register interest in particular messages, and we won't send them to you if the message doesn't match that filter. We will not have that feature in V1, but we're working on it, and we're looking to have that in one of the following versions. Another thing that we have as a capability, and that's also another capability that the router has, is that we're recognizing that bandwidth distribution in distributed systems, specifically in distributed systems where you're interconnecting applications really across networks, is that bandwidth distribution is usually unfair. So very simple example, personal example, I own two broadband connections. One I don't literally own, but I pay for it. One is at my dad's house, and one is at my house at home in Kirkland, Washington. At home, I'm blessed with a 15 megabit symmetric Fios connection. It's awesome. In Germany, there is a 1 megabit up, 16 megabit down asymmetric ADSL connection. If I push very hard from my house onto that connection, or sorry, if I push push very hard on that connection, the bandwidth distribution is kind of unfair. For any scenario where you have, for instance, let's say a mobile client, which is on a 2G network, which wants to get data in a one-to-one scenario or a one-to-many scenario, and the service wants to go and just offload that data into the system and then just walk away, where you have this unfair bandwidth distribution where you can send at a higher rate than receive it, we can make the wire longer. So the router has a built-in capability to buffer up messages and simply make that wire a little longer so that the sender can go and send in bursts, and then the receiver receives it at its own speed. So it's a mix of a direct connection and a queue. So that's another pattern that we have. Now comes the source slide. Also, something that we aspire to do is complex message processing. Complex message processing means really content-based routing, transforms, filter, enrichment, reduction of messages, really going the extra step and making the message processing more intelligent up in the cloud. Because so far the capabilities are, we have some routing capabilities, we have some queuing capabilities, and we have connection capabilities. But then once you want to do more advanced patterns, if you want to implement complete itineraries, as they're called, as one of those patterns, up in the system, then you need to have more advanced capabilities. This is why we have workflow. This is why we have the workflow service that's part of .NET Services. Now, the story is this. We went through, we have every 6 weeks just about customer events, and we have every quarter year, we have a formal SDR, software design review, with a lot of customers. Unanimous feedback from everybody is, don't give me anything that's not Workflow 4.0. Because the customers that we've talked to have said very clearly that they're excited about Workflow 4.0, they're excited about the capabilities, and they really want to have the Workflow 4.0 capabilities. And so we asked them, currently our workflow service is built on .NET 3.5. Do you want that? Do you want us to work in that? What do you want us to invest in? And the clear answer that we've gotten so far is, do .NET 4.0. That changes the prioritization for us, because we need to wait a little bit until the Workflow 4.0 stuff is available to us, and we need to build a bunch of infrastructure around it to have that super scalable cloud host for it. So what's going to happen, likely, and that's all not decided, and now the marketing people are going to stand up and going to start beating me. What's going to happen is the workflow service as it is there will likely stay in a CTP mode through the end of the year and into next year. It may actually even go away for a little while, but it'll come back. It'll come back, and it'll likely come back in a slightly different form. It'll come back as a feature of the service bus, as really message processing feature of the service bus, because that's our original vision for the workflow service. So it's not going to be your universal workflow host for the time being. That is not to say that we're never going to do that we're never going to put a universal workflow host up there, but its first mission is to actually make message orchestration easier and allow you to do declarative message processing. That's the mission. Since we can't make that switch because we have that dependency, and we've clearly heard that feedback, we're sadly saying, okay, we can't. This doesn't make sense. Let's put that on the back burner for a little bit, and let's go and make that work really well with 4.0 with a lot more activities. So that's why I'm not talking so much about the workflow service here, because we just want to be focused on getting a great service bus and a great access control service out in by the end of the year. So, the namespace. How do you map things into the system? How does that all work? We have a system called the service registry. That's the first big feature of the service bus. Whenever you register at azure.com, this translates into microsoft.com/azure/netservices.mspx, which is long, so that's why I'm saying azure.com. When you go to azure.com and you register for the .NET Services CTP, you will be asked to then create a solution ID. That solution ID ends up where we have my app up there. So you get http myapp.servicebus.windows.net, and that gives you a route for your applications. What you get is a hierarchical naming structure that you can shape in any way or form for your apps. It's a different way to look at URIs. It's a different way to organize your things from what you commonly know as URIs, because usually URIs are there to describe tightly collocated resources somewhere in a web farm, usually. So they point into a database or they point into a file system. But here that thing is a little different. Let's look at what I mean. So first of all, it's a hierarchy, so it's obvious that all these individual paths map very nicely to a URI. And then what it really is that you can host services anywhere. I said anywhere. Anywhere. That you can host services anywhere and just plug them into that namespace. It's irrelevant where they're located. They can all share that same namespace. So let's say you have multiple sites where you run applications, and you want to go and organize them by location. By service first, and then by location first. So we would have contoso.servicebus.windows.net/ERP/New York City/Chicago/San Francisco. That's one way to organize those things. Or you can simply just put the endpoints there in some other form. We also allow you to do, oh, by the way, I just want to make sure that I get enough mileage out of this. Observe the animation. The animation cost me an hour of my life, so I just want to play it twice so it's worth the money. That's tough. See, when I retire, I'll be a PowerPoint MVP. Yes. So the service registry gives you a way to go and publish metadata or endpoints or primitives into that namespace that you create. Metadata, you can go and post simply into that registry with a simple post request. What I mean with metadata is you can take an Atom entry using the Atom publishing protocol, and you can go and just post that at a place in the service registry at a place. And what can you post there? You can post a endpoint reference, WS addressing endpoint reference, in the Atom entry as an extension, which means you can use this instead of as a hierarchical version of a service registry like UDDI. You can post endpoints there. Or you can put simple alternate links, so links to other places. That's like an HTTP redirect site. So the service registry acts more or less like a registry. Now, what it doesn't have yet, and what we're still looking to implement, is categorization, being able to just tag your entries and then do a search, do a flat search over that service registry, so it really acts like a registry system. That is something we have on the list. We're going to get done, and I have my lead dev is sitting in the audience. He's looking at me like this. But not in V1. Happy? Good. The service registry is also your gateway into managing messaging primitives such as queues and routers, which I'm going to go into more detail a little later. The service registry is implicitly managed by the WCF listeners. So if you put a listener up in the system and you listen on the service bus, then you automatically get registered into the service registry, and that management all happens under the covers. What's the programming experience like? It's WCF, mostly. For the most part, for the listener part, if you are using WCF today, you know how to use the service bus. What we just bring a bunch of bindings, which are the relay bindings, and you can use those instead of the bindings that you use currently on premise or alongside of them. So if you have an endpoint, let's assume you would have a WCF service today that's using a NetTCP binding to do communication. You can add a parallel endpoint for the same functionality that exposes that information through the service bus, so you can listen on your local network as much as you can listen on the public internet out there. There's a question which I will happily answer. Yes, sir. How does the service bus play with the WCF router? You mean the new capability in 4.0? I consider ourselves a very vast superset of the WCF router. How does it play with it? I don't know. Because we're testing against, so the thing we're building and testing against is currently 3.5, because there's a natural lag in how we adopt things, because since we're building software that is designed to run on 100,000 machines, we're a little worried about adopting things that's not quite shipping yet. So we're a little slow adopting. That's the same reason as with workflow. Like, it doesn't make sense for us to take a hard dependency on those things unless they're done. And we want to reduce the number of dependencies. We have some pretty experimental stuff under the covers that we're using on the server side. We don't want to have too much experimental stuff. So the answer is we're not testing that yet. But I believe the WCF team is actually making sure that it works. I would be surprised if it wouldn't compose. So the way the programming experience works is really identical. The way you think about the service bus and how the service bus works in general, I'm going to go into more detail, is if you're just using an HTTP service today, what you do is you walk up to HTTP sys, which is the kernel level listener for HTTP in Windows, which sits there and listens on port 80, port 443, or whatever you tell it to. And you walk in there with a name pipe and stick that into HTTP sys. And you say, I want to have a lease on the following namespace. And then whenever a request comes in onto that namespace, onto that subtree, is sent up your name pipe. What our bindings do is exactly the same. They create a pipe, here a bidirectional TCP socket, or a thing that looks very closely to a TCP socket, and puts it up to a listener that isn't on your local machine, but it sits up in the cloud. So we take the traffic, and then we send that to you just as much as that name pipe sends that traffic to you. There's a little more to that. It's not the exact same mechanism, but the same kind of principle. So we have, so I have So we have symmetry with all major WCF bindings. So we support W's 2007 HTTP binding. We support the NetTCP binding, and it's always called the NetTCP relay binding. So all the bindings that you may use in your applications, if you're using WCF, we support all of those. We support W security with all the bells and whistles. If you want to go completely crazy, including Geneva framework and all those wonderful things, to completely encrypt your traffic, please go ahead. We're staying out of the W security headers. We're not doing anything with them, and so that you can use them. You can cryptographically prove to yourself that it's impossible for us to look into the body of your messages. or to inspect the headers that you send us. We will not go and manipulate. We will not go and manipulate those messages. You can see that because we're not breaking any of the signatures. We support binary, so binary encoding. We support text encoding, so text encoding for HTTP, binary for TCP communication. We support streaming. We support a reliable session. And you don't have to configure anything on your network to make that work. The demo slide comes a little later, but I want to make a point about the streaming thing. So I have 2 apps running. My machine just has decided that it wants me to log on again. Good, here we go. So I have 2 apps that I'm currently hosting. The other one is an application that we have in the SDK that's called SimpleShare. So if you want to, if you have a phone you can type it really fast, or if you have a computer open and you have an internet connection, just feel free to go to this place, clemensv6.servicebus.windows.net/share, and then there's a feed, and we can go and traverse that feed. And then we can go to documents and pictures and videos. And then we're going to pick shopping holiday. And of course, those things are really only efficient when I had multiple machines sitting here. This is why I'm inviting you to go and just poke at the service, because you can prove that to yourself. But I'm just pulling that video over through an HTTP request through the service bus. So that's a multi-megabyte video, and I have successfully streamed hours and hours of TV recordings through the service bus without any further issues. So it's a completely streaming-enabled platform, if that's something that you need, and you can realize that through the WCF support for streaming, or the WCF support for stateful sessions, where you basically just slice your streams up into smaller chunks of data. So how does this work? How is the magic performed behind the scenes? It's actually not that difficult. We have a receiver, and the receiver, the application that I'm running, starts out by creating a connection into the system, and that's a bidirectional TCP connection, or something that is like TCP. Something that we haven't talked about at Mix, that I'm happy to talk about now. I'm probably going to blog about it too. Is we have a cunning little trick inside the March CTP, which we completed, where we can actually go and create something that looks like a TCP socket over an HTTP connection. So if there's a set of ports we require to be open, so that we can go and create that connection, outbound. The ports are 828 and 808. Commonly just 828, that will work fine. If we find that those ports are closed, we're going into sneaky, trying to be clever mode, and we'll try to get a bidirectional socket going through HTTP, which is, at the bottom of it, it's just a pair of, we're playing YouTube. We're going to do a very long upload and a very long download, and then we have a bunch of software sitting around those two connections, which goes and massages them and writes the data out in the right way, has a little bit of framing on it. So we're making it look like a TCP connection. And if it falls over, we're going to build it again. So that's something that we do under the cover. So one of those types, typically just a normal TCP socket or that kind of tricky thing, is built up from the receiver side. That now gives us a way from the server side to send you data back. When that connection collapses, we're going to build it again, and we're going to retry and retry and retry. So if you create a listener like that and you put your machine to sleep, and you wake that machine up again, it's going to listen again. So that's the first thing we built. And when we built that connection, we also put in a registration for that name into the service registry, which says, hey, here's now a listener of this type that's sitting in there, and that's using that name. If you say in the policy, hey, I want to have this thing discoverable in the service registry feed, we can make that thing discoverable. Now the sender comes in and sends data to one of the other nodes in our scaling fabric. And there's several hundreds of those machines that are sitting there in every scale unit, and your solution is assigned to a scale unit. So you're using one of several hundred machines. And so you're listening on one machine, because that socket needs to have a home. And the sender is coming in through some other machine. So now we need to go and join those two places up. What happens then is that the forwarder basically goes and says, that's great, I have someone who wants to talk to you, and sends a control message. That control message is then being sent to that receiver, and now the receiver says, oh great, someone wants to talk to me, and thus a rendezvous connect back to that forwarder. So that's how we're knitting them up. We're likely going to optimize that protocol to make it more efficient, to eliminate that reconnection hop on a per session basis, and move that up and move that extra leg up into our routing fabric to make that a little more efficient, specifically for HTTP. But that's the general principle of operation. So there's an outbound connection, and also that second connection, that rendezvous connection to snap that socket, that is also outbound. Because they're all outbound, there's no need for us to connect anywhere inside. So what we have, what you don't have in most of those connectivity scenarios, is we have public IP addresses, and we have something running up there. And so we built that bridge between you and and whoever wants to talk to you. So outbound connections only, and now at that point, when that sort of sinks in, people get a little nervous about, oh wait, now you're just defeating my firewalls. Well, I'm not. I'm replacing your firewalls with our firewalls. So what we're really creating is what we have here is an externalized demilitarized zone. The Microsoft firewalls around the data center and the Microsoft intrusion detection systems and all that security gear that we have in place is now sitting there protecting your endpoint as it protects Microsoft.com, as it protects all the other assets. So your endpoint is not at all less secure than it was. You could argue it's more secure. Now it's reachable from the outside world, which makes people naturally nervous. None of those endpoints is ever sitting there unsecured unless you want it to. By default, all endpoints are protected by the access control service, and that means you need to provide a token, an access control token, for accessing those services. The access control service is built so that it can federate with systems that you have on site, like with Active Directory. So you can take your Active Directory identities, you can federate them with the access control system, and we'll then be able to go and integrate that properly. Again here, so if you have heard so far, and if you're reading documentation on the access control system ICU, on the access control system on the web, you see that the access control system is very focused on the federation angle. And that's what it will continue to be. When we ship, that's the other part of the story. One thing that's really, really hard from an engineering perspective to get right is the story for how to do distributed federated authentication using HTTP. There's all kinds of things, OAuth, OpenID, and all those mechanisms. We need to have a way to deal with that kind of authentication in the right way so you can expose and consume REST services and you can protect them. It's an unsolved thing because our security people are looking at OAuth, for instance, as a protocol and find it terribly lacking in certain aspects of security. So they don't believe it's a viable option for us. So we're making investments in that area to really make that portion right. We know that there's a lot of people who are interested in enterprise federation scenarios. However, most of those scenarios to have that rich support for it require server products such as the upcoming Geneva server. So what we're doing is we're trying to go and align with the adoption of those technologies and say, let's do the service bus coverage first. Let's do that right and make sure that the service bus is covered, that applications can talk through the service bus. Let's then, as a next step, think about how we take people identities and federate them right into the system and do that right. We know how to do it. It's just in terms of prioritizations, we currently prioritize applications over people because we believe that people are currently, you have good mechanisms to go and protect your people resources and map them to application accounts as you do that for, let's say, SQL Server or some other middle tier technologies. So we're prioritizing protecting the service bus over the federation integration, and that will then come online shortly after we release the first version. So several demos to list on the service bus. We already saw that streaming demo. I'm going to show you a few more, and then we're going to go and dive into the routers and queues in a little more detail. So I already showed you this with the video. I already showed you the other one with the blog. So let's go and play with that a little bit. So here's this blog site. And again, I already have, I procured some third-party confirmation that I'm not cheating here. The gentleman up here was so nice to pull that up on his iPhone. The gentleman over there too. So you can get to that place, and this website is hosted right here. How do I prove it? Let's go and pick the app. That's SimpleShare. So first of all, you see there are some exceptions that are being thrown because there's some filtering going on. So let's go and shut that down. So that app is now gone. What that app is a reverse proxy, which simply, I have that blog site running on my local IIS. I have that application sitting up there, and that's just getting REST requests, and I'm translating those REST requests into, well, just requests down to IIS. So I have a very cheap way of integrating here. And let's go and now hit it again. So I'm simply doing F5, and gone. What I'm getting instead here is an Atom feed with no content. If I go and start that again, which is going to take a tiny little while, it needs to go out, acquire a token, register the stuff on the service bus. The time to acquire a token actually takes a long time right now, and the rest of the service bus connectivity magic takes a very short time right now. So that's another thing we want to go and fix about the access control service to make it a little faster. So whenever you see very long latency, that's all the heavy thinking about the cryptography that happens on the security side. And so I can go back and pull that blog up again. And the title already came around here, and this is not cached, this is actually live, and if I wanted to, I could actually go and edit an entry. So it's not, I'm just not showing things, like post also works. This is just a completely transparent website hosting story. This is not the primary use case, right? The primary use case is to expose services of all kinds. Turns out that a REST service which spits out HTML is also a wonderful REST service. So just to illustrate that, I built that sample, and that was something that also inspired a lot of people. So here you have a publicly visible website hosted from a notebook at TechEd and I could actually go and disconnect that machine, wire it up to the same wireless network that you're on, and that would still work. Let's take another thing. So let's shut this down. You can still get at this share if you wanted to and play some videos. That's no problem, or music. Let's go and get another one. Let's try this. And that would be wonderful if it was there. Let's go and try find it. I renamed the directory, so it's right here. So this is a direct connection sample that shows that one wonderful trick with where we go and create that direct peer-to-peer connection. That is not nearly as sexy as the other demos, just mostly because now I'm all in console application land. The reason why our demos are very boring to look at is that we're A, server people, B, we have no talent for it, and 3, we don't want to go and distract from the purity of the awesomeness of the technology we're building. And so we're always suffering from, how do you effectively demo TCP/IP? I can connect between 2 places. Wow! The bad thing is this, and I apologize to the people who are watching the video. Those demos get kind of old after a while because you show a new way to connect, and there's 2 things popping up in console windows. So let me go and run this, and I'm going to show you what the core part of it. So here's the service that's running, and here comes, oops, and I actually need to go and enter my. That would have been embarrassing. So that's the service that's running. I got to wait a little bit until that's started because the client will run. Oh, no, I don't. So, and here comes the client. I'll show you the code in a moment. So the interesting thing here is really the client. What that does is now it's sending messages through the service bus. And we'll try to negotiate or figure out where the other party is. And you see all of a sudden that gets faster, significantly faster. So there's a set of algorithms here that allow the following trick. All data is being communicated through the service bus as you create that channel and start sending. So that goes through our data center, and therefore you saw latency induced and throughput, bandwidth induced, a limited availability of, limited throughput in terms of messages. We then look and talk to the service bus from both parties, from the client and from the server, from inside that channel and say, what is that other party that I'm talking to? So we're establishing common knowledge about who they are. Then the algorithm goes and says, could it be that we are on the same subnet? So they're checking that. If they are on the same subnet, they connect directly. If they're on the same machine, that's kind of the same thing. If they're not, then we go into the net dance where we try to go and predict how the nets will behave. And then we try to create that direct socket. So we're going to make a number of attempts to actually go and create that direct connection. Once the direct connection is established, you get the most direct, most highest throughput link between 2 places. So you're taking the data center out of the equation. What's interesting here is that we're also, since you're no longer communicating through the data center, you also don't use any of the data volume that we charge for, because we can't meter those resources. That's a reason why we will charge for premium services on a per message basis, because we got to make a buck too. But if you want to send gigabytes and gigabytes and gigabytes of data between 2 places, or in a distributed consumer scenario, we will try to get you off our data center because we really want to get you. If you do very, very high bandwidth applications, we don't want you. Like, we don't want you to go in through our data center. We want you to do direct connections. We are happy enablers of that scenario. So that program is pretty simple. We create a service host of type hello service. I don't have to show that to you. It's simply just hello has that one method. And what I'm adding here is I'm adding a credential behavior that basically just has your username and password for the service bus. That's your credential that you use. And I'm opening that service on an address that's composed of the prefix SB because we're using a TCP connection, and your solution name and the path name hello service. And really, the way this is bound is that we have a binding, NetTCP relay binding in this case, and we're using this hybrid connection mode where we're then automatically upgrading. What's also noteworthy about the upgrade is this upgrade can happen mid-message. So if you're sending a really large message, and that's what you start with, if we can get that upgrade done, we will upgrade that data stream mid-message, and you won't see that. So when you run this sample at home, because you can, it's part of the SDK, you will notice that this notification, the upgrade notification, which actually, by the way, comes from here. So there's this iHybrid connection status thing, and that's an interface that sits inside the channel, so you can get that from a property in the channel here. And so you basically just hook up to that event, and this is spitting out this upgraded notification. You will notice that we're sending the upgrade, actually the higher throughput lags a few seconds behind the upgrade notification. What happens there is we drain out the sockets that go through the relay. So we stop sending on both sides, but we're still reading, we're draining them. And once they're drained, then we actually go and upgrade the rest of the connection. So that's how this gets a little slow during the upgrade and then speeds up, and then you get the normal throughput. One thing that also illustrates in terms of the throughput that we just got, that is actually not that bad. We got, 600 messages per second through the relay, and then 2,500 local. That's not so much of a big difference. With a highly optimized application, and we're going to put some of those out as samples during the course of the summer, you can build a pure streaming application which is focused on binary data with throughput of multiple megabits per second. I've tested personally through the production service up to 12 megabits because that's the fastest connection I have available through actually at my house. And so you can build very, very fast apps. Forget the fact that this is all about that we're using SOAP messages. Once you use the NetTCP relay binding, what you're really getting is you're getting a highly optimized package format, which is using binary and which is using dictionary compression. So once you create a session, all that XML goo, the XML tags and the XML namespace expressions and all that stuff gets loaded up in a dictionary on both sides. It's kind of like Huffman compression. And then you only send tokens. So when you go and I have an application that does that for video streams, in fact. I can do HD video with transfer overhead of about 3 to 5% at most. Even though I'm shuttling that through SOAP messages, which usually makes people shudder, but only when you know how the binary transport, how the binary encoding for XML works, you realize that that overhead is actually not that big. And I would challenge you, go and build a simple WCF service with the standard NetTCP binding, and then look at it with Wireshark. There's not much XML to see there. This looks completely binary. You will have a hard time finding the boundaries between messages if you run that in session mode. So you build a sessionful transport, which then gives you all the gains of that model. So let's look at two other primitives. I have a lot of slides for those, and I have 10 minutes left. I thought for many of you, this may be the first exposure to the service bus, so I want to go in more detail on the other things as I would have done had we had more sessions. So here's the queue. The queue is something that's not like the listener. So we've so far talked about the listeners. The queue is a standalone capability of the service bus. You can walk up to any name in the service bus and apply a policy to it. We currently have a choice of two policies. There's a router policy and there's a queue policy. When we look into the future, past when we ship and when we do one of the next upgrades, there will be a message processor policy. That message processor policy will likely contain some XAML. And that's the way how you put the workflow into the service bus. There may be some other primitives that you can go and invoke by just applying a policy. So how does it work? You create the manager, whoever owns the queue, picks a name in the namespace and creates a queue policy and uploads that queue policy into the namespace. How does that happen? With Atom Pub. So you use the Atom publishing protocol, you post an entry to a name in the namespace, and that name becomes a queue. Then the sender goes and sends a message into that queue using NetTCP or NetTCP one-way binding, or using plain HTTP, or using SOAP 1.1, SOAP 1.2 HTTP, and simply sends a message to that address. That message then gets stored in that queue. Then the receiver comes and does a dequeue, which can be done in using a SOAP protocol, which we yet have to document, or an HTTP protocol, which I'm going to have on here. When I say yet have to document, that's not something that we're hiding because we're evil. That's something that we're hiding because we don't think we're done yet with that thing. So when we ship, that's all going to be out there, and you can, if you don't like our API, use our protocol. So in the service registry, which is this Atom feed, this is how they manifest. A queue has a title. So here in this case, it sits at solution.servicebus.windows.net/my /queue. And then it is represented this way. It's got a self link. This is how you manage that queue, how you can go and get at this metadata. It's got an alternate link. This is where you send data to. That coincides with the actual URI of that queue. And then you have a head for that queue. So I'm showing you the REST protocol for this. Because we want to keep symmetry between SOAP and REST, and we believe that the REST protocol here is relatively simple to use from any kind of platform, while the SOAP model will be more sophisticated for more sophisticated apps. So we have a simple thing, we're going to have a more sophisticated thing, and we're going to have symmetry in terms of overall capability, but we'll probably have the SOAP model be always a little more advanced, a little more sophisticated, just because it's a more flexible thing. It's something we can do more with. And then inside of that sits the queue policy. And before I go into that, let's go and skip those slides, and I'm just going to show that to you in code, how that works before I get to routers. So I'm going to show you the HTTP queue sample. I said I'm going to show you the HTTP queue sample. And we're going to start with the sender as soon as Visual Studio comes around and wants to talk to me again. Interpretive dance? Ah, there it is. So ask me for the solution name, ask me for my solution password, creates a queue URI, which is a HTTPS with the solution name and the name myHTTPQ. Then I'm getting the authentication token. That's a token that I'm getting with using a particular URI. I'm not going to show that. That's one of the mechanisms we're going to replace until V1. So we currently have a mechanism which is something that we're not very happy with, and as I said, we're going to fix that REST model, and so that's one of the areas of investment that's going to be changing. So there's no point in pointing that out. You can see that in the documentation, and then I go and try to get at that queue. So I try to go and find that queue. If I go and look at how I try to get at the policy, then Visual Studio doesn't cooperate again. There it goes. So let's go to the definition here. What we're doing is I'm getting that queue URI, so the URI I just created, solution.servicebus.windows.net/myHTTP Now, I want to go and discover that, so I'll go to the service registry, and I want to get that Atom feed where that queue is listed, the thing that I just showed you on the slide. So I go to the parent of it and say, enumerate everything that you have. So on the parent URI, what I'm doing is I'm doing a get, and I get that feed. Now I take the Atom feed formatter and simply read from it. I read that Atom feed in, and then I'm simply doing a query and say, hey, I need that item where the alternate link is the queue URI that I'm looking for, and where it's the same, where the path and the authority is the same. So I'm just looking for that URI. And please give me that. Once I have this, I want to get out the policy. So I'm extracting the policy. I'm extracting out the queue head URI. We're going to get to that point in a little moment. And now, once I have the queue, let's assume the queue already exists. I would get that. If the queue doesn't exist, then I'm going to set the expiration time here on a brand new queue policy. And then I'm just going to create the queue. And creating the queue is take that thing, put it into an Atom entry, and just post it. So it's that easy to create those artifacts. And then we're just going to go and put data into a message. We're going to put data into that queue. So I go Clemens v6. And can go and that's the receiver, because I just started this consumer first. So let's go and start the sender too. That would be very helpful, because I was wondering why I couldn't enter anything. That's simple share. That's not the right one. That's that. There it is. So now we have those two little apps, and now I can enter the text to put into the queue message, and it doesn't work. Well, if I had done something right, which I haven't, you would see those things coming up on that other window. Since that's not happening, you have to imagine it. And that's okay, because it's an SDK sample. You can prove to yourself that it works if someone is at the wheel who's not as stupid as I am. So that was the queue. Horrendous failure. There's going to be a Twitter entry that says #ClemensFail. So that was the queue. The queue is a queuing mechanism that allows you to just put messages into queues, and you can bring up the consumers at any point in time. And there's two ways to dequeue from it. You can do a destructive read, which means you walk up to the head of the queue and say delete. And you get on the delete, you get a returned entity back, which is your message. Or you can do a post which says, hey, I want to go and get that message. I want to look at it, and please put a lock on it and hide it for everybody else, and then I'll tell you if I have consumed that message. So it's a peak lock mechanism that we have, and that gives you some reliability. So that was queues, and now routers, and that's the last thing I'm going to say. I don't want to keep you from the party. A router you can go and create in the similar fashion. And what the router is you send the message, and you have one of multiple subscribers. You can have many subscribers in there. And we can go and just push that message to you if you open up a listener, a net one-way listener, into the router. What we can also do is if you already have a public endpoint sitting somewhere, and you just want us to send the data to that public endpoint, and so you just want to front that public endpoint with us to anonymize your endpoint, or because you want to go and fan out that data across multiple sources, then you can do so. You can create a subscription into the router, send the message out, and then we're going to go and push that to you via HTTP. You can go and embed information into that subscription that allows us to go and embed HTTP headers and or SOAP headers into the outbound message on a per subscription basis, so that if your endpoint is secured and it requires a secret token, you give us that secret token, we give you that secret token back in the header. So we can even send to places which are not publicly accessible for someone who doesn't know that secret, which could include pre-authentication HTTP header. So that's that, and there's more detail, and I already showed you that in the slide deck. What I would recommend is that you go to azure.com. If you haven't done that yet, you go and get the SDK. You download the samples. So the samples that I had to skip now is the router sample, unfortunately, just because I talked a little too much. And so you can get that there. You can try it for yourself. You can prove to yourself that that stupid 500 error that I just got is something that's not going to happen to you when you run that sample. And our call to action is build some apps. Try some things out. We think is very valuable for all kinds of scenarios of where you want to bridge from the cloud into local applications, where you want to bridge between applications, where you want to reach into destinations that are otherwise not reachable. So we just encourage you to try those things out. We will be commercially available by the end of the year. That's at least what the current projection is, and I'm feeling pretty good about this. Pricing will be announced way before that in a few months, so that you know what you're dealing with. And if you have questions, I'm happy to answer them when you find me. Come to the front, or we can walk to where the goods are now a little later. And with that, don't forget to do the evals, even though you go to the party. Stop by one of those things, because remember, I get paid by points, and I give you kickbacks. Thank you very much.